All right. Happy Halloween. I went out the door and totally forgot I didn't have any plans to dress up, but did not even think about it this morning. But nice that at least one of you tried to get extra points. And all right. So today I'm going to go over the solutions to homework 3 with you. Also happy to answer any other questions you might have about the exam. What you can expect is a lot like what we had last time. Several questions, probably each with multiple parts. I'll do my best to make sure that if you get part A completely wrong, you still can show me that you know the right process for part B and get most of the credit, kind of thing, right? That's my intent. If I royally mess that up, then that's kind of on me to fix it for you. But in general, that's my plan, is to allow you to kind of see how these problems build and challenge you to get each piece correct. But also, the most important thing is that you're showing me that what you've learned by stepping through them. Okay, so that's going to be the kind of the approach. A lot of these questions that I'm covering today will be like the types of things you might see on an exam. If they were particularly involved, maybe I would scale it back a little so that it's more manageable within the hour and 20 minutes you have. Yeah, so I think that's about it. So then next week we have the exam Tuesday. No in-person class Thursday. I sent you an email about that, so you have that information. That'll essentially be on the Flint water crisis, and up to you to watch a lecture on that at your pace. And then I guess a week and a half from now, we'll come back and start talking about wastewater. Okay, and the exam next week is not going to be cumulative, except that, of course, the things we learned about the different reactor types, of course, apply, right? So in that sense, yes, cumulative, but we're not going to test on sedimentation or coagulation or anything like that. The final exam, by the way, will be partially cumulative and partially just dedicated to the wastewater. And as you're seeing, it all kind of builds on the mass balance sort of stuff. So it's, that's kind of the plan for the remaining exams. Okay, so problem 1 says, let's compare the difference between a plug flow reactor and a CSTR for use in disinfection operations. A reactor is being designed with a criterion of achieving a 3 log reduction, so that's 99.9% reduction, meaning there's 0.01% remaining. So it might be handy to think about that. The inverse of reduction, how much is removed, as a fraction is 1 minus that, is the fraction that remains, right? So 0.999 removed means 0.001 remaining. Okay, and that's reduction of cryptosporidium using ozone as a disinfectant. And we are given a coefficient of specific lethality of 1.78 liters per milligram per minute. We're told to assume that the coefficient of dilution is 1. The process, if the flow rate for the process is 0.1 cubic meters per second and the ozone applied has a concentration of 0.42 milligrams per liter, then we have to answer the following questions. So part A says, how much crypto will a CSTR with 100 cubic meter volume remove? Okay, so clearly we've got a mass balance to solve. The context here is CSTR versus plug flow reactor, and we're going to start with a CSTR. So we can go ahead and draw a little diagram. We know it's well mixed. We've got water flowing in and water flowing out. Volume here is 100 cubic meters. And our target is that 3 log reduction, but we're given, the first problem is saying, well, given some situation, what's the result? How close are we getting to that target, right? So got to catch that. What the question specifically is asking for here is how much will it remove? And a good way to respond to that, because we don't have we weren't told there's 1,000 crypto bugs, right? Crypto spores or whatever. We're asked how much is removed. It's got to be some sort of fraction or percentage, right? How much removal? So let's get a n over n naught. This is the how much remaining. So let's try for an answer for removal would be 1 minus n over n naught as the amount removed. And we could multiply that by 100% to get it in percentage units. Okay? So that would be a reasonable way to decide how to solve the problem, set up a mass balance so we can compare n to n naught. And I think the best way is probably to go ahead and solve it for n over n naught, and then do 1 minus that, multiply by 100, and we'll get a percentage removed. Okay, so we can start answering the problem here before even doing any calculations, just with the setup to know what we're looking for. Okay, so we're given a few other things for the reaction here. We're given this K value. This is 1.78. And the units for this are liters per milligram per minute. We are given a flow rate. That was 0.1 cubic meters per second. So we notice already we have seconds and minutes. We'll probably have to do a conversion there at some point. And let's see, what else do we have? We could go ahead and calculate the K star, which is K times C to the n power. We were told n is 1. And if we calculate that, that should come out to be 0.0126. And if we go ahead and put it in seconds, that's 0.0126 per second. So what I did there was I took the concentration of ozone, multiplied it by that K that we were given to get the K star. And I converted from minutes to seconds. Okay, so that's one convenient piece. Another piece that might be helpful before we even set up our mass balance is to go ahead and get theta, since we have V and Q. We could say pretty easy to see with our volume as 100 and our Q as 0.1. That's like taking 100 multiplying it by 10, right? So we can say theta should be 1,000 seconds. Okay, so we've got several pieces now that we might need to work with. We could have waited to solve these till we saw we needed them, but I just like to go ahead and write out what I know and get the pieces that might be useful. So let's set up a mass balance then. We know we have Q and some initial concentration, bless you, and some Q and a concentration leaving. Right, so that's going to be our typical mass balance for this CSTR. We're going to assume it's at steady state, and we're going to have some concentration for the disinfectant, but assuming that we're not given any information about the ozone decaying or anything like that, we can assume it's constant, which is why we could go for the K star. So here we assumed the ozone concentration constant. Okay, so our mass balance then will be our accumulation rate is going to be what's coming in, Qn naught, minus what's going out, Qn, plus whatever happens to be reacting, which is disinfection killing stuff. And this will be in that volume K star, or we could write K times C, right? We're just inputting that Chick-Watson kinetics reaction value, right? K C to the n power times n to the 1 power, because it's first order. And if we notice the K star units are per time, so here it makes sense that this has to be a first order equation. Okay, so this should look very familiar. We've done this quite a lot, and we can solve this for n over n naught. And a nice way to do that using theta is to go ahead and divide everything by Q. So we can say 0 is equal to n naught minus n minus V over Q is theta, K star times n. From here, it's not too difficult to separate like we've done in the past and solve for some function of n over n naught. Right, so if we get the n pieces by themselves, we'll just add them both to the left side. We get n times 1 plus theta k star equals n naught. So n over n naught then will be equal to 1 over 1 plus theta k star. Okay, so with all of that, we already solved for our k star and converted the units to seconds, and we have our theta in seconds. If we didn't, now would be the time to do that, to make sure our units are going to line up properly. And if you look, it's pretty simple to see how the units have to line up, because n divided by some other n is going to be unitless. So the left side is unitless, the right side has to be unitless. 1 is unitless, divided by something else. This has to be unitless, especially because we have the 1 that has no units, right? That one right there, I didn't write any units for it, so what can we add to the 1? It has to be something that has no units. So theta times k star has to cancel out their units, right? So then theta in seconds can cancel with a k star that's in per seconds, and we're good. If 1 was in minutes and 1 was in seconds, we would see it if we write out the units very clearly that we need to adjust something. Okay, so n over n naught then is going to be equal to 0.0743. And remember, this is the amount remaining. It's the fraction remaining. But we were asked how much is removed. Well, we could say 1 minus 0.0743 is going to be 0.926 removed. So as a fraction, that's the amount removed. We could multiply by 100 and say 92.6% of the cryptosporidium are removed. Okay, now we could ask ourselves, just thinking about the bigger picture of the question, how close is that to the 99.9% we wanted? We're a little far off, right? Even for a 100 cubic meter volume reactor, that's not so great. And if you think about it, it makes a little bit of sense, because the CSTRs, we have some amount coming in. It's instantly mixed throughout, is the assumption, even if it's a huge reactor like this. That means some part of whatever's coming in is immediately going out. So you'd have to have a huge dilution in order to get that to 99.9% removed. Whereas a plug flow reactor, we'll see, we can have that change happening the whole time through the plug, through that plug, or through the pipes, or whatever you want to call it, through the reactor, before we reach the end, and there's no mixing for that end condition with the starting condition. So it's a little easier to get that larger removal value with a plug flow reactor. Okay, so then the next question is exactly that, right? How much is that going to remove? So we still have a 100 cubic meter reactor, and we could draw, if we want to, a fancy little reactor, saying this looks something like this, where we are having plug flow going through. Let's see, we'll have to do this. Something like that, right? And probably there'd be a little better of a reactor. But we'll have flow coming in, Q and naught, flow going out, Q N, still a volume of 100 cubic meters. A lot of the other parameters are the same in terms of the theta, still V over Q, which means that's 1,000 seconds. The same K star that we solved earlier will apply. Again, we have to assume that ozone concentration remains approximately constant through this. Maybe that's not exactly true, but it's probably true enough. And we could also design it, if we wanted to, by how much is coming out at the end, and say that, use that as our constant. That kind of builds in a safety factor. If there was a little more up front, but we just use the ending concentration, well, at minimum, it was that end the whole time. And so if anything, it did a little more than that. So we're not going to worry ourselves too much with that. We're just going to say that K star is still the value we solved for earlier. Where did that go? 0.0126 per second. Okay, the difference here then is we are doing a mass balance on a plug flow reactor. So that means we're going to do essentially a batch reactor, except time is going to be our theta. So we're going to say, we don't have a steady state within the plug. So the concentration of our crypto will be changing in the plug, but as a net, the whole system will achieve a steady state. So the way we can write this is as if we've got a little batch reactor traveling through, right? So we're going to do that and say in that volume, our dN dt will be equal to the decay reaction occurring in that volume, which will be the K star times n to the 1 power, right? That's our reaction function. So the V's cancel, we can solve, we've done this also quite a lot, and we can solve for n over n naught relatively easily. And we integrate this, we get the natural log, so that n over n naught ultimately becomes, would you guys like me to walk through that? Yeah, okay. So we'll cancel the V's here. Then we will integrate from the starting n to the finished n. We're going to get the n's by themselves. So we'll divide both sides by n. And then on the other side, we're going to get the dt by itself, and anything, if we had a t in the function, it would go over there as well. So k star is a constant, so it can stay outside of our integral. And we're going to integrate from 0 to time theta dt. So when we do the integration on both sides, we'll start with a simple one. The right side, that's K star times theta minus K star times 0. Right, so that 0 term goes to 0, and it's just K star times theta. On the left side, the integral of 1 over x dx is the natural log of x. And when we take that from n naught to n, that becomes the natural log of, n minus the natural log of n naught. We do a little bit of the algebra here to say that's the same thing as saying the natural log of n over n naught. So that's the process we do. I'm sorry, I'm missing the negative here. So this is the process where we get our natural log of n over n naught is equal to K star times theta. Now, we've done this with batch and called it T, right? So we can substitute there for the theta. Okay, so from here, we can get the n over n naught by itself. That, again, is the fraction remaining. So n over n naught, if we raise e to the power of both sides, that gets rid of the natural log. So e to the power of negative K star theta. And at this point, we're basically ready to find our solution. And just like we did last time, the K star times the theta, those units need to cancel, so we need them both in seconds, or we could put them both in minutes. That'll give us the fraction that's remaining in this condition. Okay, so you can see it's a very parallel process to what we did in the CSTR. It's just the mass balance itself is the difference. When we do this solution, we get a rather small number. This is 3.88 times 10 to the minus 6 as a fraction that is remaining. Now, I suppose we could put that into a percentage unit. Well, that's the amount remaining, so we have to check the amount removed. So 1 minus n over n naught would be the amount removed. So 1 minus that value is a value that's quite close to 1, right? It's going to be 0.99999, 22. Okay, so that's the amount removed. We could also say that's 99.9992%, right? So that's going to be our fraction removed. And now it kind of makes sense why we say that we call this like a 5-log removal instead of a 99.9999. You know, gets a little repetitive there. So let's make sure I got that right. So we could write it either way. What we see in total is this is a much more efficient way to remove the cryptosporidium, right? Especially because we probably don't need that much volume. If we're getting that much overkill with 100 cubic meters, we weren't even getting close to our target with the CSTR, and we're well past it with a plug flow reactor. Okay. Any questions that make sense? Okay, so then part C goes at just that. Well, what is the minimum volume required to get that 3-log removal? So here we're just going to set our condition to that 0.999 removal. So the amount remaining should be 0.001. That's because our 1 minus n over n naught, the amount removed, should be 0.999 as a fraction, right? That's the 3-log change. That's how we interpret it. That's how we describe it. So we are setting then our condition that n over n naught needs to meet this. And so then the question is, what is the volume? And the way we can answer that is to first ask ourselves, well, we're not changing the flow rate. So how do we find the volume, or how do we change it in this situation? Well, we can change theta, right? So by just simply writing theta, like last time we had our mass balance solved for n over n naught in function of theta, we could just put in V over Q there, right? So we're going to say that n over n naught, which equals 0.001, should also be equal to e to the minus k star times V over Q. Instead of putting theta there, we put V over Q. And then in this condition, it might actually be easier to solve if we had left it with the natural log. So I'll just go ahead and take the natural log of both sides to simplify it back the other way and say the natural log of 0.001 should be equal to negative k star times volume divided by flow rate. And we can solve for volume. Volume then should be Q times the natural log of 0.001 divided by the k star. Need a negative here too. Okay, so with that, we really didn't change too much. We have to go back to the Q that was 0.01. We were given this, sorry, 0.10 cubic meters per second. Fortunately, that's already in seconds, and we solved for k star in seconds, so we are basically good to go with our numbers. At that point, we can solve and find V is equal to 55.4 cubic meters. All right, make sense? Okay. So the next question, we have chlorine used as a disinfectant. You're going to add it in the form of sodium hypochlorite, NaOCl. It's going to dissolve completely to give us sodium and OCl minus. The form of chlorine is then determined given a known equilibrium reaction, that's HOCl in equilibrium with H plus and OCl minus. That has an equilibrium constant, Ka, of 10 to the minus 7.54. The disinfection reactor treats a flow of 2,500 liters per minute. And we are tasked with a few questions here. So part A says, if the pH of the treated water is 9.6, what will the ratio of HOCl to OCl minus be? So we did this, I think some practice of this in class in a problem or two. So what we're looking for is some ratio that gives us HOCl to OCl minus. And really this is going to be a molar ratio because we need to know kind of that molar basis. So as soon as we add our sodium hypochlorite, our bleach, we get this equilibrium. It actually doesn't matter how much we're treating or how much we put in, we're just going to have an equilibrium. And the equilibrium is going to be determined by that equilibrium constant. So if we know the pH and we know that constant, we should be able to solve this answer without any of the other numbers yet. So we just have to recall that the Ka equation is going to be the products over the reactants. So the products for that reaction here on the right side, the H plus times OCl minus, and we're going to divide that by the reactant, which is in this case is just the HOCl. So the question is asking for what is the ratio of HOCl to OCl minus at a given pH, right, at pH 9.6. So this equation alone is already just about getting us there in terms of answering this part of the problem. So what we can do then is rearrange this to say, well, let's go ahead and put it in HOCl divided by OCl minus. We can do that by dividing both sides by OCl minus, multiplying both sides by HOCl, and then we need to divide both sides by Ka. So we're just going to rearrange a bit, and we'll get H plus divided by the Ka. Right? So we can just rearrange that equation algebraically, and that's going to get us our solution here. So we can write this out and say, using that, we'll say this is going to be pH is 10 to the minus 9.6. So that's for the H plus concentration. And Ka we were given as 10 to the negative 7.54. When we solve, we put in those numbers. We can even just eyeball it and say that top number is a bit smaller. It's a more negative exponent, or the exponent is a larger negative number. So we'll be left with something like 10 to the minus 2-ish, right? Just eyeballing it. That means that we should be something like 0.0 something or 0.00 something maybe. So we put it in our calculator. This should become 0.0087. So that's the ratio. We could, if we wanted to, we could do some conversions and like get the equation for the total amount and get some sort of percentage. But this just asked for the ratio, right? And so this is just a ratio, which should be the answer. So the ratio is nice and simple. If we did need the fraction, like the fraction of total, that's slightly more complicated, but certainly we can do that. We just need to add that second equation that says the total is the HOCl plus OCl minus. So then we have two equations. Okay, does this make sense? All right, good. So then part B says if operators decide that a concentration of 2.5 milligrams per liter of HOCl must be applied to the treatment process, how much mass of NaOCl, so what we're saying here is this is the disinfectant, and we need some amount of disinfectant in order to achieve our desired result. We're going to add it as NaOCl, and the question is how much should we add per second if the pH is kept at or lower than 7.3. So the pKa, that Ka value is 10 to the minus 7.54. pKa therefore is 7.54. So one thing we can say without even doing any math is what we're describing here is at least just over half of the chlorine is in the good stuff, is in the HOCl form. So that's one thing we could put in our mind, but we're going to do do the chemistry to do this properly, and we'll get all these pieces together. So one thing to remember is our Q for this was given at 2,500 liters per minute. Our equilibrium reaction essentially is HOCl is in equilibrium with OCl minus and H plus, like we were doing last time. We're going to need molecular weights. So the molecular weight for, I'm going to write this out a little lower here. Molecular weight for, start with NaOCl, should be 74.45 grams per mole. And then the molecular weight for HOCl is going to be 52.45. Okay, so we need essentially two equations to solve the chemistry part of this problem. Just like in the last part, we needed the equilibrium reaction. This time we're going to have to bring in a little bit of our, the second equation as well, which is the total chlorine. I'm just going to call it total OCl, or maybe we could just say total Cl. What I'm referring to is all of the active chlorine species, which is HOCl and OCl minus. So that is equal to HOCl plus OCl minus. What we're doing here is we're counting the number of molecules, right? So we add it in the form of NaOCl. That becomes OCl minus, and OCl minus gets into equilibrium with HOCl. So when we add it in the one form, then it comes to both forms. Well, the total we added is going to be constant. We added some amount, and that's going to be distributed between these two types. It's not a huge difference, but it's important that we have that distinction. Okay, then we also have the second equation, which is our equilibrium equation. Ka is equal to H plus times OCl minus divided by HOCl. So we can use both of these together to ultimately get the fraction that is HOCl and move from there to solve for that 2.5 milligrams per liter that we need. Okay, so with that we can say the total amount of HOCl, if we look at how much is required as a concentration, we know we have to get 2.5 milligrams per liter, but what is that in moles per liter? Well, we can multiply this by 1 gram per 1,000 milligrams. And we can multiply this by 1 mole per 52.445 grams per mole. When we do that division, just grams. I already put the moles on top. So 52.45 grams per mole, if we invert that, we can say that's 1 mole per 52.45 grams. Okay, this will give us a value of HOCl value that we have to achieve. The target, if we solve that, that should be 4.77 times 10 to the minus 5 moles per liter. So that's essentially our target concentration. Does that make sense? So whatever we do, we have to achieve that. Okay, so when we go to figure out how much total we need to add, we can come back and consider that this NaOCl, if we solve for that, we have to solve for it in mass, but first we can find this as a total molar and then convert that into the mass, the total mass we had to add per time. So the total amount of chlorine of anything we have in the solution is coming from that NaOCl. So then we can set up our mass balance in terms of that total, and I'm going to go ahead and put it in brackets. So the total molar concentration we know is going to be HOCl plus OCl minus, right? So I'm going to go ahead and put in that number we just calculated, 4.77 times 10 to the minus 5 moles per liter, plus whatever OCl minus is. Okay? Once we get those two pieces together, then we can solve for the total NaOCl we had to add, and then convert that to mass, and then account for the flow rate to get our mass per time. Okay, so right now we have two unknowns, right? We have the total and the OCl minus. So we can take a look and use our second equation to give us a way to solve for OCl minus. So I'm going to rewrite this here and say total is going to be that 4.77. And here I'm going to substitute, because what we can do is solve this second equation for OCl minus. And that will give us the same, that'll give us an equation in terms of H plus, which we know, Ka, which we know, and the HOCl, which we just solved to say we need at least this much, right? So that's, those are all knowns. So instead of writing OCl minus here, I'm going to say we can multiply both sides by HOCl and divide by H plus. So we end up with Ka times this HOCl, which I'm just going to go ahead and write again, the 4.77 times 10 to the minus 5, divided by, we had to divide both sides by H plus. And we know the H plus should be 10 to the minus 7.3 because we were given the pH, right? So with this, we actually can directly solve for the total concentration of chlorine that was needed. So total will also equal the moles per liter of NaOCl that we add, and that's going to be 7.51 times 10 to the minus 5 moles per liter. From here, we can solve for the mass. So we take that. That's going to be moles of NaOCl, or moles of total chlorine. So we'll take 7.51 times 10 to the minus 5th moles per liter of NaOCl. And we can multiply this by the molecular weight inverted. So we'll take, well, no, we don't need to invert it. We just multiply by the molecular weight. 74.45 grams of NaOCl per mole. Per mole of NaOCl. Okay, so that we can then solve. This should give us a value in grams per liter. This is 0.0056 grams of NaOCl per liter. We could maybe put that in milligrams if we wanted to, but we're going to do the how much per time in a moment anyway, so maybe it'll come back to a, we'll leave that off for a minute. So this many grams per liter, so now we have to multiply this by how many liters we're doing per time. So multiply this by our flow rate, should give us a mass per time number. And then we'll see we have to convert from minutes to seconds. Because we were asked to give this in seconds, I think, yeah. Okay, so we'll take that 0.0056 grams per liter, multiply this by our 2,500 liters per minute, and let's go ahead and multiply by 1 minute per 60 seconds. That'll give us seconds on the denominator. That should give us a value of 0.23 grams every second. Or we could write that as 230 milligrams per second. So we were just asked for mass. It wasn't specified, but did specify seconds. So either of those would be just fine. Okay, does that make sense? Yeah.
So whenever the NaOCl disassociates, like OCl is left over, where is it getting the H to create HOCl? Is it from the water?
Yeah, it's a good question. The H is just coming from the water. So there's always going to be some H or OH minus available because H2O is in equilibrium with H plus and OH minus. Now there's not usually a lot of them, but that is how the pH scale is created, is that balance there. It's a good question.
So you never have to worry about how much H is.
Not for our purposes, really. Now, if you recall, probably the first homework, I gave you some question about you're adding this much acid. It releases a certain amount of H+. That's going to move the pH. So sometimes you might realize that what you're doing, the disinfectant that you're applying, might end up shifting the pH. But for this, the scope here, and for what I'm looking for you guys, I'm not really worried about like how much is that consuming, right? We're not going to go quite that far into it. It's a very good question, though. Anything else for that problem? All right. So problem 3 said we had a membrane filtration unit treating water in rural areas lacking major infrastructure. Gravity is used to drive water through a 0.22 micrometer membrane. The unit houses 22 square meters of membrane area. Membrane is operated in a cross flow under constant flux regime to meet a demand of 500 liters per hour of water. The treated water is 30 Celsius, and there's a note that says the pressure of 1 meter of water is equivalent to 9.8 kilopascals. Okay, so the first part says what is the flux across the membrane given the parameters provided. And I asked for an answer in meters per hour to 3 decimal places. Okay, so generically we know flux is flow per area. So we can start by just saying, well, we're looking for a flux. This is going to be a function of the flow rate divided by the area. Now, the flux across the membrane should be the amount of water that passes across the membrane, right? So that should be the Q in the permeate. Remember, we can draw a membrane schematic, something like this, where if we have cross flow, then we have 3 flows. One is across the membrane and leaving. That's the permeate. The feed, of course, is feeding to the membrane itself. And then whatever hits the membrane and leaves and doesn't go through, that's our retentate. Doesn't really matter which diagonal you use. It's convenient to use a box with a diagonal, but just as long as the permeate is what is crossing your membrane that you drew. Okay, so we'll say QP then. We could label each of these with a flow. That's what we have to consider. Now, in addition to that, the problem itself says we're meeting some demand for water, for treated water. That means we have to provide that much water. That means we need that much water in the permeate. So we already know the QP should be 500. So we can just go ahead and say this is 500 in liters per hour. And we were also given the membrane area, 22 meters, square meters, right? We're asked to give an answer in meters per hour, and we have liters and meters right now, so we need to convert the liters into cubic meters, and then we're basically good. So we can say, take this and multiply that 500 by 1 cubic meter per 1,000 liters as our conversion, and that should give us our answer. So J then should be, the flux should be 0.023 meters per hour. Okay, so quite simple. And one thing you'll notice here is there's a fair amount of information just giving you the context, and at least so far, not a lot of it was needed, right? We didn't actually need anything with the pressure. The membrane size might be good context, 0.22 micrometer. So if you ever work with membranes, you'll kind of have a good feeling for what that is. But I don't think I gave you anything to do with pore size of a membrane in terms of that effect on our calculations. We could go there if we took a deep dive on membranes, and the membrane scientists do a lot of that kind of stuff. But I don't think we're relating that unless I tell you, for example, the pore size has this relationship to resistance or something, and then you know what to do with resistance. But yeah, that's not something I'm planning to do for you. Okay, so the next part says if the recovery rate for the membrane is 95%, how much water must be fed to the membrane unit to achieve the required permeate flow? Okay, so again, the required permeate flow, that should be the 500 liters per hour. Now, water recovery means how much of the water that we gave to the membrane is now useful. So we could do this quite intuitively, or we can recognize we have an actual formula that just writes out explicitly that intuition, right? This recovery R should be QP divided by QR. So how much, QF. So how much are we getting out the permeate divided by how much did we feed it? That's a fraction, that's a ratio. So if we take that 95% and convert it to a fraction, 0.95, that's our R, lowercase r. So we can very easily solve for Q feed then, which is the desired answer, and say this is going to be that QP divided by 0.95. And if you think about it, this answer should be a little bit above 500, right? Approximately 5% more. So if it's not, then we have some trouble, because logically it has to be more. So we do that, we should find a value of 526.3 liters per hour. Okay, so pretty straightforward, just a matter of interpreting what the problem is saying and what's needed from you, right? Any questions, issues? All right. Part C then says when the membrane is clean, membrane resistance is 1.8 times 10 to the 13th per meter. Remember, this is kind of a funny sounding number because it's so big, but our membrane separation later would never be a meter, right? So it's, whatever it actually means, it's talking about a small sliver instead of a full meter. Okay, how many meters of water, this is talking about height to feed it, that pressure, are required to pressurize the membrane to yield 500 liters per hour of water, given that particular resistance. So here we need a different equation for flux. So here's where we involve that pressure across the membrane and the resistance, now that we're dealing with that stuff. So we have the equation flux is equal to the transmembrane pressure divided by the total resistance times the dynamic viscosity of water, right? That's our equation there. We can solve for the transmembrane pressure. That's going to give us our height, right? So this is kind of the question. what's the pressure required? That's going to tell us how much height is required. So we can solve this. We can rearrange this equation and say that's going to be our flux times the resistance times the mu. Okay, so when we look up our mu, we should find at 30 Celsius, that's going to be 0.798 times 10 to the minus third kilograms per meters second. So we can solve for the transmembrane pressure. That should give us, when we put in those numbers, because we have the RT, now we have the mu, and we know the flux required. We calculated that in part A. This should be 90.7 kilopascals. So the height we can find, because we were given in the first part of the problem, we were told that 1 meter is equal to 9.8 kilopascals. So we can take that 90.7 kilopascals and multiply it by 1 meter for every 9.8 kilopascals. So the height then should be 9.25 meters. Okay, make sense? I don't know why, but I'm just really proud of this mu. I don't know if I've ever drawn one so nicely. It just came out and I was like, oh, that's perfect. Okay. Part D then. We say, during operation, the membrane fouls continuously such that there's some resistance added over time, right? So we get 5 times 10 to the 12th per meter added every 20 minutes. So then the question says, how many meters of water will be required to supply the same 500 liters per hour after 1 hour of operation? So we let it go for an hour, we're adding some resistance over time. How high is that water stacking up in order to push the water through? So basically just looking at the pressure change when we increase the resistance. And maybe there's room to get into like a kinetic reaction with this added every 20 minutes, but let's not go there. Let's keep it simple. Didn't say this was any sort of a first order thing. Let's just say 1 hour, that's 60 minutes, means we've added this 5 times 10 to the 12th 3 times during that period. If we wanted to really be fancy, we would need to do some sort of kinetics on that, but let's just keep this kind of simple and say 5 times 10 to the 12th per meter times 3, because 60 divided by 20 is 3. So we could say times 60 minutes, and we're adding that 5 times 10 to the 12th every 20 minutes, right? So that's why we're multiplying by 3. So the resistance, we'll say R from fouling is going to be equal to that 5 times 10 to the 12th times 3. So the R fouling is going to be 1.5 times 10 to the 13 per meter. Now we were told the start, we could call the resistance for a clean membrane was, what was it? 1.8, thank you. 1.8 times 10 to the 13 per meter. So now we can, previously that was the only source of resistance. Now we have a total resistance, which is just all the individual pieces added together. So we should end up having 1.5 plus 1.8, 3.3 times 10 to the 13 per meter. Then we just solve the problem again, just like we did previously, and say we have transmembrane pressure. We can set that equal to the flux times the total resistance times mu, and we will find that that should be 166 kilopascals. So we just basically changed the RT and then compute it again, and we're going to then solve for the height one more time by saying that's going to be 166 kilopascals divided by that 9.8 meters per kilopascal. That should give us 16, almost 17 meters. Okay. Good? Does that make sense? All right. So, last problem then, we have a granular filtration system. So a surface water treatment plant is being designed and will employ granular filtration as part of the treatment train. The plant needs to produce 0.65 cubic meters per second of treated water. Consulting company has been contracted to design and install filters that will be 7 by 10 meters in size and provide a loading rate of 9 meters per hour with a 72-hour cycle time. That includes 20 minutes for backwashing and 15 minutes for rinsing. So first part says, what is the effective filtration rate, R effective, for these filters? So we have an equation for that, if we recall. So R effective should be the volume of the filtered water minus volume rinsed minus the volume backwashed divided by the area of one filter times the total cycle time. So we need these pieces then. We're going to need each time that we have. We're given all those. We need to put everything in the right units. We've got minutes and hours. So we ought to get something. Our loading rate was given in meters per hour, so maybe that's a good target to give our effective loading rate in those same units. Okay, so we've got a few things we need to write down. So the area of a filter, that was given as 7 by 10, so that should be 70 square meters. We were not given any information about the backwashing rate, so we will assume it's equal to the loading rate. That's the best thing to assume unless you're given information about it. Total cycle time we know as 72 hours. The time for backwashing, that was 20 minutes, which means 0.33 hours. Repeating. Time for the rinsing was 15 minutes, that's 0.25 hours. Quarter of an hour. Did not have any air purge. And so then all we need to do now is solve for the filtration time, which is going to be 72 hours minus the time we spent doing the backwashing and the rinsing. So that'll be 72 minus 0.33 minus 0.25 hours. So the filtration time then should be 71.37 hours. Okay, with that we can solve for all the volumes and put in our equation for R effective. So we've got volume filtered. We can start with that one. That's going to be our loading rate times the filter area times the time spent filtering. Put all those numbers in. We get 44,933 cubic meters. 993, excuse me. We can do volume that was backwashed. I could write all this out again, but instead I'm just going to say the answer here, 210 cubic meters. because that's going to be the volume, the loading rate, or the backwashing rate in this case, which is equal to the loading rate, times the area of the filter times the time backwashed, should give us 210 cubic meters. The volume rinsed should be pretty similar to that, right? It's 5 minutes shorter, so it should be a little less. That comes out to be 157.5 cubic meters. Okay, with all of that, we are ready to solve for the effective loading rate. And before we even put in the numbers, we know this ought to be a little slower than our filtration loading rate, our generic loading rate. So we put this in and find that it is 8.8 meters per hour, which is a little bit less than our loading rate, so we are happy to see that. If you got 9.2, that would be trouble, right? So we can't have an effective loading rate faster than our filtration loading rate. Okay, part B then says how many filters do we need to meet that flow that's required. There's a couple ways you could approach this. The algebra should get you to the same place regardless. So we need a Q total of 0.65 cubic meters per second. We've got loading rates in the effective loading rate in meters per hour, so we'll probably have to adjust that. Just going to write that up again. That was 8.8 meters per hour. We could get the flow rate for one filter. That should be that R effective. And this will be a net flow rate across time. The average flow rate that one filter produces, we can solve by taking the effective loading rate times the area of the filter, so 70 times that 8.8. And then we can say, okay, well, how many of those do we need? So we'll take this Q total and divide it and say that's going to be some number of filters, that's what we're solving for, times kind of that effective flow rate from one filter, right, is how you could solve that. So I'm going to say this is going to be times R effective times the area of the filter, of one filter. So we could rearrange that and solve for the number of filters, and this will give us the Q total divided by the effective flow rate from one filter, essentially. So this will be divided by R effective times area of one filter. When we solve that, we should get an answer that looks like 3.775 filters, but recognize that we cannot install 0.775 filters because they are 10 by 7 meters. So even if this was 3.01, we actually need 4 filters because 3 is not good enough. We need to add a 4th. So this becomes 4, and we have to round up regardless of the fraction there to meet that minimum threshold. Okay. This does mean we have a bit of extra flow, which is the subject of the next question. How much additional flow in cubic meters per second can the plant handle before new filters must be added? So really that's just the difference between 4 and what we just calculated, the 3.775. So that gives us just a little bit of wiggle room of extra space. So we just call this the area, the filtration area that is extra, I suppose, would be 4 minus that 3.775. So we could even just put this into an area if we want, and then calculate that into a flow rate, given that we have some effective flow rate per area. Okay, so this would be as if we had 0.225 filters extra. So we can take that 0.225, multiply it by the 70 square meters for one filter, and multiply that by the effective loading rate, which, by the way, is a lot like a flux, right? So when we're doing the membrane problems, do flux, some flow across some area. Well, here we're also doing some flow across some area, as a loading rate is kind of like the flux. Okay, so this then gives us an answer for the problem to say 0.0387 cubic meters per second extra. Now, one thing you'll note that I didn't really draw any attention to, we do need to convert for both of these problems this into meters per second, right? I don't have that value written, but you just include that unit change in your calculation, and it should be fine. Okay, I think that's it, right? Any questions? Any issues? All right, is this helpful? Great. Okay, well, have a happy Halloween, and see you on Tuesday.